All right, so here we are looking at aldosterone and its effects. So when aldosterone, which is secreted by the adrenal glands, and this is showing then when your blood pressure is low, aldosterone is secreted, and what it does, it activates sodium and potassium pumps and channels which are inserted into the collecting duct. And when these sodium and potassium pumps are activated, you have increased sodium reabsorption. One of the things though, especially with sodium, in the body physiologically, well, sodium follows water and vice versa. So with the increased sodium reabsorption, you have increased water retention, and this causes an increase in blood pressure. So that's one way in which you're corrected when blood pressure is low. When your blood pressure is high, you do have secretion of aldosterone, and it also, not only does it lead to sodium reabsorption, but in the case for high potassium concentration, it leads to potassium secretion. And this causes increased urinary potassium loss. And once this happens, you have a lowering of the blood potassium concentration, right? So this is how for high blood potassium, how it is corrected, and for low blood pressure, how it's corrected through the commonality of sodium potassium pump activation. Right, so here we're looking, yes, go ahead.
So I have to be honest here, so I get another problem to see your screen because I'm on work here. I'm working and I'm also listening to you, so it was in my pocket. So it's touching in my pocket. So I'm not seeing the PowerPoint properly because it's only moving.
You're seeing the PowerPoint?
So I was trying to get it back.
Anybody having problem?
Well, I don't. Well, the rest of the class should be able to see it. It's just I remember I working and people opening the gate. I don't want
all kind of thing. I understand. Not an issue.
All that kind of thing. So who knows? It must be pressing and must cause that the PowerPoint things to be right on the PowerPoint. So I have to apologize for that.
Okay, Kieran. But one of the good things is I will record it, so you know at your convenience. You'll do it, and I'll do it right after class. In seeing that, you know, you have that situation, so it wouldn't be too long for you to, within an hour after class, I'll put it up so you'll be able to see it or review it in that regard, okay? But thanks for letting me know, Kieran, indeed. All right. So with the urine concentration, some important points to note. So this is just showing urine concentration. This, of course, is the last of the four. Remember, in terms of the functionality of the kidney, glomerular filtration, tubular reabsorption, tubular secretion, which we just looked at, and the urine concentration. And this is how urine concentration is actually facilitated. Now, the nephron loop establishes an osmotic gradient in the renal medulla. And if ADH, so the hormone that is actually present for letting the distal convoluted tubule become porous is ADH, right? ADH. And what does ADH stand for? I forgot.
Antidiuretic.
Antidiuretic hormone.
Right? Not to be confused with uncle diuretic hormone. Anti-uncle. You all are not seeing the humor in that. Let's get back to urine concentration. So antidiuretic hormone. So what we mentioned this last day, the diuretic, it does make you urinate. So therefore an antidiuretic is something that will, you know, prevent large volumes of urine from being released. So the ADH, once it is released, it causes then the reabsorption of water such that the volume of urine will actually be decreased. So if ADH is present, water moves down, the osmotic gradient resulting in concentrated urine. But if it's absent, right, the water is not reabsorbed. So it just keeps going down and is collected in via this region. They go through it by the papilla, calyx, and collects in the ureter, bladder, and is voided outward. All right. So that is very important to take note of in terms of urine concentration, how it is facilitated, right? In terms of this movement, you also have this gradient that allows the movement outward. But most importantly, the channels that are open, due to the presence of ADH. Blood pressure now. So blood pressure kidneys are responsible for those. Let's have a look in terms of when your blood pressure is low. So you have a low blood pressure. This is detected by the vasomotor center in the brain, and it could do one of two things. One, it could lead to vasoconstriction. So if your blood pressure is low, that means all of your blood vessels, they're constricted. So therefore, the low blood pressure is now flowing through a smaller volume or a smaller area. So in so doing, this actually increases your blood pressure. This could be, how could you think about this? Where when you constrict, you have the flow of something, it's going through at a constant rate, but if it now flows through something that is smaller, it goes further. Anybody could think of a parallel to that? I'm only thinking about
Yes,
something.
sir.
Go ahead.
Okay, so for instance, the water in plants with a hose, and you put your fingers over it. You put your fingers over it, so it will go further and at a
Right.
smaller. Yeah,
Thank
that's
you.
what I'm thinking.
Yeah, thanks, Stacy. Well done. Ernest?
So,
Oh, okay. I just saw your mic on, no problem. But yeah, but that is exactly it. So if you're thinking you're wetting something with a hose, the water goes a certain distance, but when you put your finger over it, you're actually narrowing that surface area from which the water is coming from, and now the water is able to go further. So that is one way in which vasoconstriction leads to increased blood pressure. Another way, of course, is increased cardiac output. The vasomotor center could actually cause your heart rate to go up, and this then causes increased arterial blood volume, and you have increased blood pressure. So that is another way of doing it. Also, in terms of with the kidneys now, you have increased salt and water retention. When you have an increased salt and water retention, this then leads, because remember, sodium, once sodium is retained, water follows it. So therefore, you retain the sodium, and by extension, you retain the water. That water now gets into your capillary system. Then from the capillaries, it gets to the venule arterioles. From the venule arterioles, it gets into your vein and arteries. So that leads to an increase in the total blood volume. And because the volume of the blood now goes up, you have increased. With the increase in the arterial blood volume, that is how blood pressure is increased. So there are three ways in terms of control of blood pressure. One, the vasomotor center could actually increase your heart rate or cause the vessels themselves to constrict, vasoconstriction. And the other way, the kidneys increase salt and water retention. When you increase the salt and water retention via the kidneys, that leads to an increase in the total blood volume. Salt and water, the salts, once the salts are retained, water follows it. And physiologically, you'd learn to appreciate that in the body, salt follows water and vice versa. Water follows salt. When you sweat, for instance, what happens, right? If you taste a sweat, sweat is salty. Salt follows water. And in this case now, you retain your salt and the water follows the salt. And when the water follows the salt, that water now could then be used to increase the total blood volume. The increase in the blood volume then increases your blood pressure. So that's just showing how those three things are interrelated. Very important to take note of.
Excuse me, sir.
Yeah, go ahead.
I just have a question, right? So, if you have like a high, say, salt intake, you have a lot of salt in your system. That could like give you excessive amount of water in the kidneys.
Right, and a very good question there, Stacy, and I see where you're going with that. Correct me if I'm not wrong. Increased salt. So what happens? This pathway then would be activated, and even though the body has regulatory mechanisms for getting rid of the salt through your urine, right? But if it's unusually high, this one will be activated predominantly. So what does that lead to? Boom, boom. So persons who do consume high levels of salt, they usually have high blood pressure. What is some of the things associated? Is high blood pressure a good situation? No. And when you do have high blood pressure for extended periods of time, what happens? It causes damage to the endothelial lining or the inner lining of your blood vessels. Same thing that occurs with when too much sugar is present. in the blood, it damages. So that's where diabetics have issues, particularly relating to microcirculation. So the circulation associated with organs like the eyes, the kidneys, anything, right? Microcirculation in the distal regions from the heart, particularly in the legs, right? In the veins of the legs. So you have damage to the endothelial linings, right? Which could lead to circulatory issues. As a circulatory issues, if you're looking at the legs, and ultimately lead to tissue damage. You know, poor wound healing, that's one of the symptoms associated with it as well. But to answer your question, yes, your body does try, if you do take in large amounts of salt, it does try to excrete it in the urine, but if it is too much, it does remain, and this pathway does follow, and it causes increased blood pressure. So you have blood pressure being high, which is oftentimes you would hear persons who do have high blood pressure, they're advised to, or they are put on a low salt diet. I don't know if I answer your question, Stacy.
Yes, sir. Thank you.
Okay, you're welcome. It's a very good question. All right. So renal blood pressure, this is showing the blood pressure regulation. So the juxtaglomerular apparatus, so these are specialized cells located in the area of the nephron, and they actually, the cells, the granular cells, they secrete renin when the filtrate volume and afferent arterial pressures are low. Renin initiates angiotensinogen activation into angiotensin 2. Angiotensinogen conversion, that's very important. Angiotensin 2 acts at multiple sites to stimulate blood pressure. All right, so that's important in terms of the working of this juxtaglomerular apparatus, which is, as you've seen here, is a set of cells which is located very close to the Bowman's capsule. So let's have a look at it. So the liver secretes angiotensinogen. This angiotensinogen, when it is detected, low blood pressure, the kidneys secrete renin. Renin acts on angiotensinogen, which is secreted by the liver, converting it into angiotensin 1. Now you have the ACE, or the angiotensin converting enzyme, secreted from the lungs, converts angiotensin 1 into angiotensin 2. This angiotensin 2 has effects, metabolic effects, and this is what it does. 1, it causes an increased thirst, stimulates water intake, or 2, increase antidiuretic hormone release by the posterior pituitary, reducing water loss in urine. 3, increase aldosterone release, increases sodium, and this is what we looked at earlier on in terms of the aldosterone release, increases the reabsorption of sodium, which indirectly increases water retention, and also vasoconstriction, the narrowing. And all of these things, you have increased peripheral resistance with vasoconstriction causing an increase in blood pressure. And these 3 metabolic processes causes increased arterial blood volume. Once the volume increases, you'll then have an increased pressure. So this is how the kidneys work in collaboration with, by extension, the liver and the lung capillary, the lungs, and the enzymes that they release, and ultimately causing blood pressure regulation. So let me just go through that again. The liver, right? So the liver secretes a base amount of angiotensinogen, into the blood. When low blood pressure is detected from the kidneys, renin is released. This renin converts the circulating angiotensinogen, which is present in the blood, it converts it into angiotensin 1. So this angiotensin 1, now the lung capillaries within the lungs themselves, they release ACE, which is angiotensin converting enzyme. And as the name implies, angiotensin converting enzyme converts angiotensin 1 into angiotensin 2. Now this, remember, this is circulating in the blood. What effects does it have? It has 4 effects. 1, it increases the thirst stimulation. So then you'll begin to feel thirsty. So by nature, you go and you increase your water intake. 2, it causes the posterior pituitary to secrete ADH, or antidiuretic hormone. We mentioned that the antidiuretic hormone acts at the level of the collecting duct causing it to become porous. And now that it is porous, we have water reabsorption. So therefore, your urine now is more concentrated because of the fact water is reabsorbed. 3, increased aldosterone increases sodium reabsorption, which indirectly increases water retention. And then, of course, fourthly, you have vasoconstriction. Vasoconstriction on its own, it increases peripheral resistance. So what it means then, the resistance to blood flow, because if you think about it, imagine then you have a double doors open and you're going to a fete. Okay, good. Everybody could run through the doors. But if now they close one of the doors and there's only one door open, right? You have a little resistance. It's a little harder to get into the fete, as it were. And that's the same thing that happens here. When vasoconstriction occurs, the area through which the blood is flowing now becomes smaller. And in so doing, when the area becomes smaller, this increases ultimately blood pressure. And these are the 3 causes. Increased arterial increases the blood volume. So take note of them. 3 of these things increases the blood volume, but only 1 increases the peripheral resistance. Ultimately though, they increase the blood pressure when initially your blood pressure is low. All right, and this is just one example here from the book, which we don't have, so I wouldn't elaborate on it. And the last thing that we'll speak to is strong and weak acids. All right, so when we speak about strong and weak acids, which one is we're talking about? Hydrochloric acid, right? Hydrochloric acid is a strong acid. It's totally ionized into both hydrogen ions and chloride ions. So HCl, where in the body would we find HCl? One word relating to digestion.
Stomach.
Thank you. Yeah, the stomach. So therefore, imagine it's a very strong acid. So how it is then that it doesn't dissolve away in stomach? Because it's a strong acid. What mechanism does the stomach have to protect the HCl, which it secretes, from destroying it? Well, it does something. It secretes a sticky substance that lines the stomach walls. And where's that stick? Oh, it doesn't make sense. Excellent response. Mucus. So mucus is secreted. What would happen if you have problems with mucal secretion? If either mucal secretion or you have, let's say, H. pylori, which is a bacteria present that could thin out the mucus, make it very thin. That could lead then to something happening to the stomach, because the HCl could now eat into the stomach wall, literally dissolving it. And when that happens, what is that situation known as? When you have, it doesn't make sense. I teach, everything is clear to everyone. Yeah, very good. Stomach ulcers. Right, so stomach ulcers, and usually with stomach ulcers, they find the existence of that bacteria usually is present in the stomach, H. pylori, right? So do keep that in mind. I know it was a long time since you all looked at that in SnF1. I just thought I would revisit it. Let's go forward. Strong acid, HCl. A weaker acid is acetic acid. What's another name for acetic acid? We use it in chow, when we make in chow or when we pickling something.
Lime.
Lime is citric acid, right? Which is a weak acid. So I will give you a tick on that one. That is very true. Acetic acid. What's another name for acetic? It begins with V.
Vinegar.
Vinegar. There we go. So vinegar is a very weak acid. What you could use vinegar for other than making chow?
To clean.
As a cleaning agent.
And so that is why, as Charles just mentioned as well, with acetic acid, with citric acid, which is found in limes. That is why it's used to clean fish and chicken. You could use either one. Either you squeeze a lime or a lemon, or if you don't have them, you could use vinegar. All right, so that's how it is, to get off the little icky stuff off of the meat, in terms of the preparation. So do recall seasoning, so you can use it from your personal knowledge, right? When you're seasoning something, you use either lime. When you don't have lime, you use vinegar, right? So both of them, they're weak acids. But the HCl, the one in your stomach, yeah, that's the strong one. All right, so do take note of those two. Right? So what happens here, right, in terms of regulation of these acids? So from your diet and some metabolic processes, well, the body compensates for fixed acids using buffers. Now, a buffer is substances which are released that keeps the pH at a specific level. It's like a police then. So the buffers are the acid police. It keeps your body within a certain pH range, and that is very important that the body has a certain pH range, particularly for some body fluids. When we think about blood, for instance, what is the manageable pH for blood? When we're thinking about blood.
1.4.
Pardon?
7.4.
7.4 in terms of the blood pH. All right, 7.4. What would happen if we go outside of there? We go outside of that range. What would happen if your blood pH hits, let's say, 7.1? What would happen? ... You'll be having a chat with your ancestors, right? So it's important, and the body has mechanisms for actually blood police, right? Or fluid police in the body, and they're known as buffers, and it regulates it. Let's see how it does. So buffers compensate by converting strong acids into weak acids, right? And so here it is, for example, the hemoglobin buffer, very important. And so you have bicarbonates, and what it does, the ions, the hydrogen ions that are produced, they now react with the bicarbonate ions, forming bicarbonate, and the bicarbonate is broken down into carbon dioxide and water. As you know, water has a pH of 7, which is manageable. That is not harmful to us. So the carbon dioxide, here it is, carbon dioxide that is produced, goes to the lungs and is then exhaled. So this is one way in terms of the breakdown of the excess acid that is within the extracellular fluids. That is how it's actually compensated for. The kidneys, of course, they secrete new bicarbonates into the blood, and that corrects acidosis. Acidosis is a situation when the hydrogen ion concentration in the blood goes up. So therefore your pH is lowered, right? So compensation, you need to compensate for that, or else you will be visiting the ancestors. So let me just say that again. So within the blood itself, there are mechanisms for compensation as it relates to keeping that blood at that specific pH, 7.4. And the way it is done in terms of that mechanism is actually bicarbonate ions are secreted from the kidneys, and these bicarbonate ions neutralize the excess acid that is present. When we say excess acid, is very important. Let's take a step back. When we have strong acids or acids, for that matter, they have that ability to break down and form separate ions, H+ ion concentration. Do remember pH. pH is really a measure of the H+ ion concentration, right? That's what the pH stands for. The big H is really for hydrogen, and P, I want to say, is Latin, that means measure of. So when you're looking at the pH, to keep that pH to that 7.4, you do have these buffers. Buffers, nothing more than blood police in this instance. And the kidneys, how does it facilitate it? Kidneys, they allow the secretion of bicarbonate ions, and these neutralize the hydrogen ions that are present in the extracellular fluid, forming the bicarbonate shown here. The bicarbonate then breaks down into carbon dioxide and water. Carbon dioxide is then secreted from your lungs, and that is how the acid content is regulated in the body. Okay. Now, the renal response to acidity is not on the syllabus, so I wouldn't get into this one. And this relates to the case of Santochi. All right, so that's it for the lecture for today. All right, and we would stop the recording at this point. There's just one other thing I want to show you to answer that question which we spoke about earlier. In terms of should we hold our pee? Is it a good thing to hold your pee?
No, sir. I believe that could cause urinary tract infection.
It is. And let's see if we could look at a short video this one. We'll look at a short video that will highlight the reason why it really is not a too good of an idea to actually to hold your pee. Yeah. Let's see if we could post it up.
Soon becomes a pressing sensation that's impossible to ignore. Finally, it's all you can think about, and out of sheer desperation, you go on a hunt for a bathroom until, Humans should urinate at least 4 to 6 times a day, but occasionally, the pressures of modern life forces us to clench and hold it in. How bad is this habit, and how long can our bodies withstand it? The answers lie in the workings of the bladder, an oval pouch that sits inside the pelvis. Surrounding this structure are several other organs that together make up the whole urinary system. 2 kidneys, 2 ureters, 2 urethral sphincters, and a urethra. Constantly trickling down from the kidneys is the yellowish liquid known as urine. The kidneys make urine from a mix of water and the body's waste products, funneling the unwanted fluid into 2 muscular tubes called ureters. These carry it downward into the hollow organ known as the bladder. This organ's muscular wall is made of tissue called detrusor muscle, which relaxes as the bladder fills, allowing it to inflate like a balloon. As the bladder gets full, the detrusor contracts. The internal urethral sphincter automatically and involuntarily opens, and the urine is released. Whooshing downwards, the fluid enters the urethra and stops short at the external urethral sphincter. This works like a tap. When you want to delay urinating, you keep the sphincter closed. When you want to release it, you can voluntarily open the floodgates. But how do you sense your bladder's fullness so you know when to pee? Inside the layers of detrusor muscles are millions of stretch receptors that get triggered as the bladder fills. They send signals along your nerves to the sacral region in your spinal cord. A reflex signal travels back to your bladder, making the detrusor muscle contract slightly and increasing the bladder's pressure so you're aware that it's filling up. Simultaneously, the internal urethral sphincter opens. This is called the micturition reflex. The brain can counter it if it's not a good time to urinate by sending another signal to contract the external urethral sphincter. With about 150 to 200 milliliters of urine inside of it, the bladder's muscular wall is stretched enough for you to sense that there's urine within. At about 400 to 500 milliliters, the pressure becomes uncomfortable. The bladder can go on stretching, but only to a point. Above 1,000 milliliters, it may burst. Most people would lose bladder control before this happens, but in very rare cases, such as when a person can't sense the need to urinate, the pouch can rupture painfully, requiring surgery to fix. But under normal circumstances, your decision to urinate stops the brain's signal to the external urethral sphincter, causing it to relax and the bladder to empty. The external urethral sphincter is one of the muscles of the pelvic floor, and it provides support to the urethra and bladder neck. It's lucky we have these pelvic floor muscles, because placing pressure on the system by coughing, sneezing, laughing, or jumping could cause bladder leakage. Instead, the pelvic floor muscles keep the region sealed until you're ready to go. But holding it in for too long, forcing out your urine too fast, or urinating without proper physical support may, over time, weaken or overwork that muscular sling. That can lead to an overactive pelvic floor, bladder pain, urgency, or urinary incontinence. So, in the interest of long-term health, it's not a great habit to hold your pee. But in the short term, at least, your body and brain have got you covered, so you can conveniently choose your moment of sweet release.
All right. So we just saw then, the reasons. So is it a good idea to hold in your pee?
No, sir. But sometimes the sleep they just be so good, you know.
True, quite true. Or I don't know if sometimes it does occur as well. You know, you might actually think you're in the bathroom and you begin to urinate only to discover, hello, I'm still in bed. Not a good thing to go through. Yeah.
Yes, I know it.
Periodically it happens. Okay, so that's it for that today. in terms of the lecture. So let me just stop here.